it. Okay, kiddos, let's talk about these type of problems. Okay, this is simply a recognizing problem. Okay, just like when you have your phone number, if you don't recognize the phone number, you probably don't answer it when somebody calls you. You let it go to voicemail and then you see who it is later. You need to recognize this as your assignment, or you are being told to take the derivative of this function. Okay, this is the definition of derivatives, difference quotient. Okay, you just need to recognize if you're taking the limit of a function, right, and you see as delta x goes to 0, so we're getting smaller and smaller and smaller intervals, right? You see your x plus delta x in here, and then you see your function here, right? So I need to finish this derivative. The general form of your definition of a derivative is f prime equals, right? F prime is the derivative, okay? But it's not put on there. They want you to be able to know that this whole entire limit stuff, this whole entire equation is asking you to take the derivative, okay? So the definition says that we're taking the limit as some random variable goes to 0 of, the function is f of x plus h minus the function itself over h, right? This is the form for the definition of a derivative, right? F prime, the derivative equals the limit. So we have two values. We have the x value and we have the h, right? So we're basically having a secant line. So let me see if I can draw this. So we have an x value here maybe, and then we have an h value over here, right? So this is your x plus h. And right now we have ourselves a secant line because we're involving 2 points. And what's happening is this distance right here is getting smaller and smaller and smaller, right? As h goes to 0. So we're bringing in our point, our secant line is getting closer and closer and closer until we're close enough that it looks exactly like a tangent line, right? And that's what our derivative is. It's the slope of the tangent line at any given value of x. Okay, so that's what is happening. That's what this part means. We are evaluating our function at smaller and smaller and smaller intervals, right? So basically we're having f of x minus f of x, right, which is going to be 0, of course, and the bottom is 0, right, which is our strange, our limit definition here. So what's happening is we want to look at this, right? Recognize our form of your definition of a derivative, and it's asking you to take the derivative of that function. The function is the thing that comes after the minus. Okay, so what here in number 1, what function comes after the minus? Cosecant of 3x squared. So we're basically being asked to find the derivative with respect to x of cosecant 3x squared. Okay, so this is not a quotient rule, right? This is not some crazy derivative thing where we're going to actually try and evaluate it. We need to recognize this as being the definition of a limit for this particular function right there. So now that we understand what we're supposed to do, how do we take the derivative of cosecant of 3x squared? Well, this looks like it's, of course, a trig one. So first we're going to take the derivative of cosecant, and then we're going to apply the chain rule, because basically every single trigonometry is going to be a chain rule derivative. So the derivative of cosecant is negative cosecant of whatever's in your parentheses times cotan of whatever is in your parentheses. So this all belongs to cosecant only. Okay, so we have not messed with the 3x squared yet. So that's the derivative of cosecant. All of this is just the cosecant part of your chain rule. That's the cosecant part. The derivative of cosecant is negative cosecant times the cotangent, right? And we got that by using the quotient rule for 1 over sine. That's what we did, is we took the derivative of 1 over sine, because that's the reciprocal of cosecant, and we came up with negative cosecant times the cotangent. So now we're going to use our chain rule and take the derivative of 3x squared, which is 6x. Okay, which is a perfectly wonderful answer, but if you want to write it as the algebraically correct way, we would put the 6x in front, and then we would have the cosecant of all this stuff times the cotangent of that stuff also. Okay, so this would be the way that you'd see it on a multiple choice test. It would have the algebra in front and then the trig second. Remember, this is all multiplication. We are multiplying all these things together. Okay, so it's really important to recognize in calculus what these equations are telling you to do, because they're not going to explicitly tell you to do anything. You need to recognize what it means. Okay, so having done that, hopefully the rest of these are going to be pretty easy. So looking at this, right, it's the same equation. Limit as delta x goes to 0. So here's your f of x plus h. Here's your function, right? So this is asking us to take the derivative of e to the 2x. That's what it wants us to do. Just take the derivative of e to the 2x. Okay, so once again, all e's are chain rule problems. So the derivative of e to the anything is itself, exactly what you started with. And then we multiply it times the derivative of your power, which is just 2. Right, the derivative of 2x is 2. So our final answer would be 2e to the 2x as the derivative of that, of e to the 2x. Okay? Recognize that form, the limit, the definition of a derivative form. The limit as a number goes to 0, right? So on this third one, what is the function that we're taking the derivative of? Natural log of 2x cubed, right? It's pretty easy once you recognize what this is asking you to do. This is saying take the derivative of natural log of 2x cubed. The derivative with respect of natural log of 2x cubed. Okay, so this is a natural log derivative. So hopefully you've memorized the form of the natural log derivative, which is 1 over the argument of your natural log, so 2x cubed, exactly how you see it, right? That is the derivative for natural log. And then we have to multiply it by the derivative of your argument. So what's the derivative of 2x cubed? 6x to the second power, 6x cubed. Now let's see what kind of simplification we can do here. So we have 6x squared in our numerator divided by 2x cubed in your denominator. Okay, 6 divided by 2, that's just going to be 3, right, in the numerator, because 6 is bigger than 2, so the bigger number stays on top. And we have x squared in the numerator and x cubed in the denominator. So I can take away 2 of them, so my final answer is 3 over x. Right? It's a pretty nice, cute, simple derivative for this really complicated looking initial starting problem. Okay? So recognize what you are being asked to do. Number 4. What is our function? Sine squared of 4x minus 2. So we're taking the derivative of sine squared of 4x minus 2. So this one is definitely a chain rule problem. Okay, this is all kinds of, in fact, how many functions are there here? that we're going to be using in our chain rule. How many chains do I have to link together?
3.
There are 3 of them. Sorry, the first one is the square. The square is the first thing that we're going to take the derivative of. The second thing is the sine. We're going to take the derivative of our trig. And our last thing is going to be the 4x minus 2 on the inside. Okay, so I've told my students that whenever we have a power on a trig, that we can write the power on the very outside. So we put the whole entire trig thing into parentheses, and then we raise it to the second power. That's the same thing, right? It doesn't look as mathematically beautiful, but mathematically that is the same thing. So this is what we're going to take the derivatives of. We start with our power. So the 2 comes to the front. So 2, then everything else stays the same. The sine of 4x minus 2 raised to the first power. But of course, we don't ever raise something to the first power that looks like prime and other different things, so we don't do that. Okay, so there's our 2. We have taken the derivative of our squared function. Now we take the derivative of sine, which is cosine. The derivative of sine is cosine of 4x minus 2, right? So next we do sine. The derivative of sine is cosine, and it's multiplication. So there's not a plus or a minus, it's all multiplication. And our last chain is the derivative of 4x minus 2. And the derivative of 4x minus 2 is 4. That's a great looking derivative, right? Chain rule. Expect to see these ones. Anytime we have a trig raised to a power of an equation, you're going to have 3 parts to your chain. So your final answer can be 8, because 4 times 2 is 8, times the sine of 4x minus 2, times the cosine of 4x minus 2. All of it is right there. So speaking of recognizing a form, what do we see here, right? What is this one asking us to do? So this form is asking us to take the derivative. Well, okay, we're trying to evaluate the derivative at a point. Okay, so we're taking the derivative and then we're evaluating it. Okay, this is called the alternate form of the derivative. So here's your alternate form. So the limit as x approaches a number of your function minus the function evaluated at that number. So this is the y value when you plug your c, right? So c is the number that or the point, the x value that we're trying to evaluate the derivative at. Okay? So we have the function is now here. This is the y value of the function, and then x minus that number again. So if we look at our equation, right, here's pi over 3. This is the point, or the x value, that we're trying to evaluate our derivative of. And what is our function? Right here. We're trying to find the derivative of sine squared at pi over 3. Okay? So this part, this is the y value. If you were to plug pi over 3 into your function, you would get negative 3/4, or you would get 3/4, right? And then here you have your c value again. So notice, right, once again, this is just something you need to notice, to become familiar with. This is us being asked to find what is the derivative at pi over 3. That is what this is asking us to find of our function sine squared. So this is our function that we are taking the derivative of. So now we just have to take our derivative. So what's the derivative of sine squared? Okay, so first we take the derivative of our power, which is 2 times the sine of x, and then we multiply it by the derivative of sine. So derivative of sine is cosine. So that is our derivative function, right? That's our equation that we're going to use to find the derivative at any point. And what point do we want the derivative at? Pi over 3. So we're going to put pi over 3 into both of these places. Okay, and I can do that. So this turns into a unit circle problem. What is the sine value at pi over 3? That's root 3 over 2. What is the cosine value at pi over 3? That's 1/2. Okay, remember this is all multiplication. So 2 times root 3 over 2 times 1/2. Okay? So this will be, if you were to multiply it all out, we do numerators times each other, right? So all these are numerators. This is just 2 times the square root of 3. And we do denominators times denominators, which is over 4. And I can reduce this by 2 divided by 4, so it should be root 3 over 2. That is our derivative evaluated at pi over 3. Okay, number 6. What is our function and where are we evaluating it? Natural log of 2x plus 2 is our function. And we're evaluating it at 2. Perfect. So we're trying to figure out what is the derivative at 2. Okay? So back to our natural log. The derivative of natural log is 1 over the argument, so 1 over 2x minus 2, times the derivative of 2x minus 2, which is 2. Okay? So we're going to move this 2 to our numerator up here, and now plug in x of 2. So we're going to plug a 2 in down here. Okay, so we have 2 in our numerator. 2 times 2 is 4. 4 minus 2 is 2. So our answer is 1. 2 divided by 2 is 1. Okay, our last example. Our function is tan squared, right? Tan squared. And our point is 3 pi over 4. Okay, beautiful. We're trying to find the derivative at 3 pi over 4. So first we deal with our power, right? So the 2 comes to the front as 2 times the tangent of x, 2 tan x. All right, so first we take the derivative of our power, and now the derivative of tangent is secant squared of x, right? And since we have an x here, the derivative of x is 1, so we don't really have to have times 1. But that would be our last part of our chain rule if that were to have been something other than just x. Okay, so our derivative is 2 tan x times secant x, secant squared. So now let's plug in 3 pi over 4. 2 times the tangent at 3 pi over 4 times the secant squared at 3 pi over 4. So now we have to do some serious unit circle action. Okay, what's the tangent at 3 pi over 4 from our unit circle? -1. Okay, the tangent at 3 pi over 4 is -1. The tangent at all the pi over 4s are 1 if it's in the first or the third quadrant, and it's -1 in the second and fourth quadrant. And then what's the secant at 3 pi over 4? So the secant is the reciprocal of the cosine, and the cosine is -√2 over 2. which means our secant value is going to be negative root 2. Believe it or not. And this thing we have to square because it says secant squared. Secant squared. So before we do our multiplication, we have to square that root 2. So simplifying, we still have, well, this is negative 2. We can multiply those together. But what is negative root 2 times negative root 2? That's positive normal 2. Positive normal 2. So negative 2 times positive 2 is negative 4. So our final answer is negative 4. Okay? So you need to recognize these two forms, the definition of the derivative and where do we find our function that we're deriving. And then our other one is our derivative at a point, and where do we find the function and what do we plug in.